welcome and thank you for being here. Today it's my pleasure to introduce you our speaker today, Dr. Oleksandr Sera. He got his master, PhD, and Doctor of Science degrees from the radiophysics and electronics from the Taras Shevchenko University in Kiev, Ukraine. In 2001, he joined the Department of Physics of the Kaiserslautern University of Technology in Germany, where he became an associate researcher in 2006, and he got the permanent position. Then in 2009, he received from the university the Dr. Habili in experimental physics. His current research topics are spin wave electrodynamics, magnonics, spintronics, spin caloritronics, functional microelectronics, and so on. He has published more than 120 publications. Among them, they have two natures, Nature Physics, 3 Nature Communications, 20 or more than that physical review letters. And today he's going to talk about room temperature Bose-Einstein condensate of magnon and supercurrents. Welcome and thank you for coming.
Thank you very much for this nice presentation. And it's a pleasure for me to make my talk in this audience in Mexico. I am for the first time in Mexico, and it's very interesting visit for me from both points of view, from scientific points of view. I also know Professor Ordonez Romero for a long time. From that time when he worked in United States of America and grew in the group of Professor Carl Patton. So it was a pleasure for me always to be in contact with him and discuss science. And also I would thank you very much for this kind invitation. And also I'd want to thanks a lot to Professor Oleg Kolokoltsev, who is working here and with whom we institute mates, and we worked in radiophysical department of Kiev's National University long time ago in neighbor labs and investigated different aspects of spin waves in yttrium ion garnets and other magnetics. And my current talk here, it will be about, as it was already announced, about room temperature Bose-Einstein magnon condensates and supercurrents. And this work was performed in Technical University of Kaiserslautern in Germany and the Department of Physics and State Research Center Optimus. And it was supported by different funding agencies. First of all, it's Deutsche Forschungsgemeinschaft. It's a scientific finance agency of Germany, and also in frame of Transregional Project 49 multi-body interactions between particles, and also it is supported by advanced grant of European Research Council, which is obtained by leader of our group, by Professor Burkhard Hilbrands. So, and before I will start my talk, I will show you this position of our university on the map of Europe, because such name as Kaiserslautern is not known normally for the audience. It's a small city, approximately 120 kilometers on the southwest from Frankfurt. And it is, you see here from this position, you can see that it is located in the center of the Europe, in very old historical part of Germany. Here it's Rhineland-Palatinate. It's nearby of such centers, as Paris, as Brussels, as Munich, Stuttgart, Frankfurt, Berlin, Hamburg, Amsterdam, London, and also even from the former capital of the Rome Empire. It was not Rome at that time, it was Trier in time of Constantine of Great. And it is placed this city nearby here. It's very, very old town, approximately 1,200 years ago it was founded. And here it's not large town in spite of its ancient one. It is approximately 100,000 people is living there, and university is rather small. It's only technical university, no medical studies, no jurisprudence, only technical studies here, biology, technicians, electrotechnical, physical, mathematical department, building engineering department, and here is the campus of our university. It is here. It's approximately 15,000 students, so much more smaller than than here. So, and it's surrounded by, it's on the border of the city and surrounded by the largest massive forest massive in the Europe, which goes from this area to Alsace and Lotharingia and to France border, and it is uninterrupted massive of forest. So very pleasant place with, as a kurort place. It's for relaxing and for doing studies. It is good prepared. And here is our group. It's rather large experimental group. And here it's Burkhard Hillebrands, who is a leader of our group. I play the role of senior scientist in this group. And it's clear not entire group works on Bose-Einstein condensation of magnons. It is, we investigate the different aspects of behavior, dynamical behavior of magnets in different areas. And here I would like to present that group which mostly contributed to my talk. So it is our PhD student Oleksandr Sera, PhD student Halina Musienko-Shmarova, our former PhD student Dmitro Boshko, who now is our postdoc, and just today it was informed he won Alexander von Humboldt very prestigious stipendium to work 2 years in Glasgow University. Abroad, and also Vitaly Vasyuchka from Kyiv University from Ukraine, who is our postdocs, and he is me. And all our success was not possible without support, strong theoretical support. And we works with, first of all, I'd want to say, with Professor Gennady Melkov from Taras Shevchenko National University of Kyiv, Ukraine, who always fertilize us with new ideas, and also with Professor Lvov and Dr. Anna Pomelo from Weizmann Institute of Science from Israel, and from with Professor Andrei Slavin, Professor Vasil Tiberkevich, both from the Oakland University from USA. I should say that both me, both Vitaly Vasyuchka, Dmitro Boshko, and Vitaly Tiberkevich are former from the group of Professor Gennady Melkov from Kyiv University. So he is really our scientific fuss. Such, and what I speak about, and macroscopic quantum states, microscopic quantum states. And the main idea, find such macroscopic magnonic quantum state for information transfer and processing. And it should be maybe in some sense analogous to superconductivity as Josephson currents and superfluidity in helium-3 and helium-4, because it's in both these situations we have a deal with macroscopic quantum states. And we expect maybe it will be free of dissipation apart from magnon-phonon and magnon-electron coupling. So the motion of such macroscopic magnonic quantum states will be viscosity free motion. Does not mean that dissipation will be completely switched off, as dissipation can occur always in the nature. And this talk will be about Bose-Einstein condensate of magnons in yttrium ion garnet via parametric pumping, and after pumping BEC dynamics and so-called evaporative supercooling of a magnon gas. I also will speak about supercurrent generation in such Bose-Einstein condensate and long-distance supercurrent transport, which is associated now by us with magnonic second sound. And if we will look from macroscopic point of view on some ferromagnet, we will see there are many oriented by external magnetic field, macroscopic magnetic moments, which can process around the direction of the bias magnetic field. And this precession is not independent for each of macroscopic magnetic moment. In paramagnets mostly, in nuclear magnets, it is independent. Here, each magnetic moment is strongly coupled with another magnetic moment through the two species. The first, it's exchange interaction, which is responsible for ferromagnetism, and second one, it's dipole interaction. It's simply magnetic field. And this magnetic field is static, and magnetic field is dynamic, because precessing magnetic moment generates the dynamic magnetic field, couples to another magnetic moment, induce motion of the second one, and so you see such collective motion of magnetic moments, which you can look at this and see it looks like a wave, so-called spin wave. And from the point of view of the second quantization, each spin wave can be splitted in quantized quasi-particles, and these quasi-particles are known as magnons. And one magnon is simply delocalized change in the orientation of one spin in such a system, which is associated with change of magnetization of one magneton Bohr. And each such quasi-particles carries energy, which can be associated with its frequency, momentum, which is associated with wavelengths of and with wave vector of such particle, and can be characterized by mass, especially in exchange area, because in exchange area, connection between energy and momentum is quadratic. It means the same as between energy and momentum for real particle. And that is why we can introduce a mass and introduce this mass here when eta is exchange interaction constant. And spin, it's clear that magnon carries spin because it is associated with spin of electron, and magnon is excitation. So if in electron initially we have spin up, and excitation of magnons gives us spin down, and 1/2 spin up projections, 1/(-1/2 spin down projections, the total change in spin is 1, and it means that magnon carries spin 1, and it means that such particle is a boson. And there is, in one state, can be gathered many such magnons. So the macroscopic quantum states are possible with such particles. Oh, okay, these particles are not independent. They interact each other mostly due to the 4 and 3 magnon scattering. 3 magnon scattering. One magnon splits in 2 magnons, or 2 magnons confluence in one magnon, and 4, there is 2 input magnons which scatters, and there is 2 output magnons. So 4 magnon interaction. So, and I told that magnons are bosons, so they carry a spin 1. And similar to other quasi-particles, as photons, Cooper pairs, for example, phonons, exciton polaritons, they are described in thermal equilibrium by Bose-Einstein distribution with 0 chemical potential. Why with 0? Okay, it's 0 chemical potential because such type of quasi-particles as photon or as magnon, density depends on thermal excitation. When we have 0 temperature, we have no excitation of such particles. All magnetic moment is oriented along the bias magnetic field. And only due to the thermal excitation, spins change its orientation from up to down, and magnon is excited. And it means if we will decrease the temperature in Bose-Einstein distribution to 0, we will have no particles. Density of particles goes to 0. And that is why chemical potential in such system is 0. That is why we are not able, when we are speaking about Bose-Einstein condensation, to reach this condensation by decreasing of temperature. Decreasing of temperature simply decreases the quantity of particles. So, and here there is the distribution calculated for, in yttrium ion garnet, calculated distribution of density of quasi-particles for some temperature and for chemical potential 0. If it would be possible to change chemical potential without change of temperature, for example, to increase quantity of particles in the system due to the external injection, in such a case, this distribution will be changed drastically. And when the chemical potential will reach the bottom of spin wave spectrum, in such a case we have here concentration, finite concentration of particles at the bottom of spectrum, and we obtain Bose-Einstein condensation. So our task to reach this state. And how we can do this? And the first, I should say that we should find the proper material for investigation. And our proper material is yttrium ion garnet. It's ferrimagnet. It means it's non-compensated antiferromagnet, and he has the rather high magnetic moment. It's 1750 Gauss, and this material is very complicated. You see here this material. Here, this cubic crystal, lattice constant is 12 angstrom. Unit cell contains 80 atoms. And in spite of such complexity, this material has the lowest magnon damping in the world. Known, lowest magnon damping. Lifetime of magnons can be here up to, in best samples, I observed up to 700 nanoseconds lifetime. And if you compare it with such materials as iron, permalloy, for example, where the lifetime will be maximum 10th nanosecond, you understand that it's the best material for investigation of dynamics of magnon gases and condensate. Why I say that it's so important, magnon lifetime? It's so important because what we should do in our experiment, we should increase chemical potential. How? To inject external magnons into the system using some athermal way. We inject these magnons. Magnons should, in order to give us ability to speak about temperature, they should uniformly or quasi-uniformly redistribute over the spectrum. They should thermalize. And for this, they need time. And that is why lifetime is very important, because if lifetime is shorter than thermalization time, we should expect for no Bose-Einstein condensation and no such effects related to the thermalization. And that is why this lifetime is extremely important. And also important that this room temperature ferrimagnet and Curie temperature is 560 Kelvin. That is why we can perform all experiments in 300 Kelvin if we want at lower temperatures, but it's simpler and more comfortable to perform the experiment at room temperature. Such one. And which material we use with this yttrium ion garnet? There is two kinds of materials. There is yttrium ion garnet, okay, 3 polycrystals, they are monocrystals, and they are thin epitaxial films. And we use thin epitaxial films. Due to the specificity of spectrum of magnons in such films, they are produced in Ukraine. Ukraine is strong in production of these materials. Previously, it was discovered in France, but produced mostly in Soviet Union and in USA in Cold War time. And Ukraine preserved the technologies of production of these good material. So we use this material with thicknesses approximately 5, 6, 10 micrometers, which is very suitable for observation of Bose-Einstein condensate. And here you can see the spectrum of spin waves or magnons calculated in 6 micrometer thick yttrium ion garnet film, which is magnetized in plane by magnetic field 1700 Ørsted. Magnetized in plane. And when it is magnetized in plane, you see that the spectrum should be rather anisotropic. Why? Spin waves can propagate along magnetization direction. Spin wave can propagate across magnetization direction. And it's clear that in such cases, due to the dipolar interaction, spectrum should be different of this. And here you see with this blue curve, the spectrum of dispersion curve of magnons which propagate along magnetization direction. Wave vector of these magnons is parallel to the bias magnetic field direction. And here, with this magenta curve, you can see the dispersion curve for magnons which propagate across the magnetization direction. It's clear there is any other abilities magnons can propagate with any other angle respect to the magnetization direction. But for simplicity, I don't demonstrate this. In reality, it's not magnetization, it's not dispersion curves, but dispersion surfaces. And here and this magenta, when angle of propagation is changed, transforms in this blue one, dispersion curve. You can ask me what these gray curves. It is also dispersion curves for magnon modes, which have non-uniform distribution of dynamic magnetization on the film thickness across the film. So here, magenta and blue, it's for uniform distribution of dynamic magnetic moment along the film thickness. It means that spins process in all positions from the bottom of film to the top of film in phase. If you have standing waves in this direction, if you have a standing waves in this direction, energy of such magnons increases due to the exchange interaction, and these dispersion curves are shifted up. Such, and so you can also look, I'm too fast, you can also look that how we can describe these dispersion curves, so how we can find the curvature. And for this we use the Landau-Lifshitz equation of precession of magnetic moment, and here change of magnetic moment of time, here a magnetic ratio gamma, and here magnetic moment and cross effective magnetic field. I say not bias magnetic field, but effective magnetic field, and effective magnetic field, it's a function of position in sample, and it's the first consists from the bias constant magnetic field, which is responsible for the magnetization, and precession occurs around the bias magnetic field, but also there is other components of in this effective magnetic field which are related to the dipolar interaction. One precessing magnetic moment generates microwave magnetic field which interacts with magnetic moments in different position of space. It is here. And also with exchange interaction. It is here such effective magnetic field which can be which we use to describe exchange interaction, saturation magnetization, and exchange constant. And here there is Nabla squared magnetic moment. So, and here what we have here plus puncts, it's maybe additional components in the magnetic effective magnetic fields which are responsible for magnetoelastic interaction, for anisotropic field, and more and more. Okay, so it's the spectrum of our in plane magnetized yttrium ion garnet film. How can we inject magnons in this system? I always told that we should inject magnons. Such. For this, we can use, for example, ferromagnetic resonance, very known instrument for dozens of years. But it's not very effective, because efficiency of ferromagnetic resonance is restricted by damping in the system, because it's resonance line. You know that resonance line gives us the damping in the system, and amplitude of resonance line is not infinity high, because it's restricted also by damping in the system. And there is another method to inject, effective methods to inject particles in the system. It's so-called parametric pumping. Parametric pumping, it means that I apply not external force to excite precession, but I change some parameter of the system. In my case, I change bias magnetic field, H0, which is not perpendicular to the magnetic moment, but is oriented along the magnetic moment, as here. And I apply the microwave magnetic field HP pumping, H pumping, along the bias magnetic field. So the field H0 now is H0 plus minus HP multiplied sinus omega pumping T. And it oscillates. And when this oscillates, we can couple to the magnons in very specific form. It is very similar to this such how these when children stay on the swing and sit down and stand up and change the length of swing. He doesn't apply any force. He simply changes length of swing. And if he does this properly, he can increase the energy of the system. such. The same the situation is here. And force excitation with swing also possible when father stays nearby and push him. It's clear when the we have strong bad swing, it is I push, I'm not able to increase the amplitude of oscillation strong. In this case, in parametric amplification, if we will pass to the system more and more energy, we can increase more and stronger oscillation. It's interesting that for parametric interaction, quantity of energy which we will pass to system depends on amplitude of oscillation. In the external force, it depends only on the external force. Here depends also on amplitude of oscillation. Why? Because if initially swing doesn't swing, it's such. In such a case, children can stand up, sit down on this swing, and no oscillation will be excited. That the first initial push is necessary. In our system, this first initial push is thermal excitation, thermal noise in the system. So, and after that, we will start to increase pass energy to thermal magnons and increase quantity of these magnons drastically. From the quasi-particle point of view, this process can be described as split of the one microwave photon of pumping electromagnetic fields in two magnons with opposite wave vectors. Why with opposite wave vectors? Because normally electromagnetic field is not very good localized in the space, and that is why it can be associated by wave vector near zero. And that is why in order to preserve momentum conservation law, we should excite two magnons with positive and negative wave vectors, so that here that wave vector of this particle should be near zero. Also, we should preserve the energy conservation law, and it means that energy of this initial photon should be twice higher than the energy of two magnons. Two magnons carries frequency F pumping over 2. Here it's energy conservation law, it's momentum conservation law. And we inject magnons in the system. When we inject magnons in the system, amplitude increases, system absorbs more energy from the external source, amplitude increases, more energy is absorbed, and when we compensate damping, so that energy can be absorbed so much that we compensate damping, density of magnons should increase to infinity. It's very effective process. Okay, infinite number of magnons not possible. The quantity of injected magnons, it's approximately 10 order 20 in 1 cubic centimeter. And there is some nonlinear mechanism to restrict the amplitude, the density of magnons. So it's not damping, it's nonlinear mechanism which should restrict this amplitude. Okay, so we know that now we inject a lot of magnons, and these magnons scatters due to the interaction with each other, and change their energies, and change their K vectors, redistribute over the spectrum. And this magnon thermalization due to the mostly 4-particle scattering occurs, and we have incoherent magnon gas here. And when, in such case, chemical potential, which was previously 0, increases above 0, and when it reaches the minimum of magnon spectrum, Bose-Einstein magnon condensate occurs in these points. What is meant by Bose-Einstein condensate? Some coherent spin wave spontaneously appears with such lowest frequency and at these K vectors. So from incoherent, from thermal noise, we obtain harmonic motion. How can we detect this? We can detect in different ways, because excitation is known, but we should detect. And this detection is mostly in our group, is done using the Brillouin scattering mechanism. And it is inelastic scattering of photons on spin waves. And it can be as absorption of one external photon and change frequency of these magnons, or emission. And here it's absorption of magnon and emission of magnon in such a case. And you obtain the Stokes anti-Stokes components in the scattered light, and these Stokes anti-Stokes components corresponds to the absorption and to the emission of magnons by photons. And frequency of these Stokes-Anti-Stokes components respect to the frequency of the probing light gives us frequency of our magnons in the system. And so the standard BLS system has frequency resolution. We can detect this frequency shift, and this frequency shift gives us for Stokes-Anti-Stokes frequency of magnons in our system, which is indicated somewhere here, and also the amplitude of these Stokes-Anti-Stokes component of the inelastically scattered light gives us knowledge about relative density of magnons at the given frequency. Not absolute, relative. And who is a specialist here in brilliant light scattering? It's Professor Ordonez Romero. He has a very good equipped lab, and I have seen this, and very well organized, so maybe we'll do some experiments later together. And here, frequency resolution. Is it enough to have frequency resolution? Yeah, for initial experiments it's enough. But you see that the spectrum of spin waves can be rather flat in different areas. And in such case, we know that the magnons are somewhere here, somewhere here, somewhere here, but we don't know exactly are they at the minimum or are they smashed over this entire region. And how we can define the position of magnons more precisely, how we can overcome this wave number uncertainty. And it's possible if we will introduce this in the system wave number resolution. And wave number resolution is connected to the Bragg scattering from the initial light. If the initial light illuminates some tilted sample, and after that reflected from the wavefronts of spin wave from the magnons, after that reflects from the underlying some type of mirror, it can be metal mirror or it can be dielectric mirror, and after that scatters back exactly in the same direction. So if our illuminator and if our detector are placed exactly in the same direction, in such case we can say that the spin wave which propagates here with this wave number Q spin wave can be found from this simple equation where is this wave number of laser multiplied with the sinus of the incident angle. So from this we can determine this wave number of this spin wave or magnon which contributes to our signal. And how can we change this sinus theta angle? In different manners. We can rotate our sample. We can rotate, for example, this probing laser beam. It was this setup has been done by our former PhD student Dmitro Boshko. I told about him. He introduced this in this very high wave number resolution. It's approximately 1/10⁵ radian per centimeter. You can compare with maximal wave number accessible in such a system, and you see that resolution is approximately 1%. So, and we should combine excitation and detection of spin waves. And here we have a laser for the detection with acousto-optical modulator. Acousto-optical modulator splits the continuous waves of light in pulses. It gives us ability to control heating of our sample. Such not to heat sample permanently, because we inject magnons also in pulses. We inject magnons, observe what occurs with the system, and after that wait for the thermalization, for the relaxation of system, and repeat our experiments. And in order to apply these pumping pulses to excite magnons, we use microwave generator, and after that strong amplifier. In such section, when we use microwave resonator to increase density of the pumping field, and yttrium ion garnet film is placed on the top, and we excite magnons, and we illuminate this with external laser light. Scattered light goes to tandem Fabry-Perot interferometer, also accessible here in the lab of Professor Ordonez Romero, and after that analyzed in frequency and angle of the incident light gives us the information about wave number. And if we have now this instrumentation in our hand, we can perform our experiment. Here it's the part of the spectrum of magnons which propagate along the magnetization direction. And here you see that in such a case we have minimum in the spectrum when we can expect for Bose-Einstein condensation. And let's look closer in this area. And if we will perform our experiment, what we can see here, you can see time, and here wave number. We have wave number resolution. And in this time moment, when pumping pulse is applied, you see this purple area here, or red area. In this moment, pumping pulse is applied and starts to inject magnons in the system. And nothing appears at the bottom. We analyze this area of the spectrum at the bottom. Nothing appears at the bottom. You see this dark area, no magnons are there. Why? Because we inject magnons not to the bottom. We inject magnons far away. So, for example, in our case, 2 gigahertz above. Because if we will inject it directly to the bottom, it will be direct excitation. It's not interesting. We inject it 2 gigahertz above. Magnons should interact each other, redistribute over the spectrum, and this needs some time. Thermalization time, I told about this. And after some time, magnons appears here. You see this green color. And they appears in the spectrum in this area first. Here, wave numbers appears. And after that, these magnons move down to the lower wave numbers values and starts to concentrate around the global minimum in the spectrum, around this point. You see here. After that, we still need to wait. And magnon scatters, and after that goes exactly to the minimum. And this red area demonstrates us increase of the magnons exactly in the global minimum position, which is indicated by the dashed line. Okay, and we switch pumping off and repeat the experiment once again. So in this experiment, Bose-Einstein condensate is formed during the pumping pulse is applied. We'd want to have more pronounced Bose-Einstein condensate in this experiment. And such naive thinking in our case, it was how we can reach this. We should inject more particles. If threshold of Bose-Einstein condensation is already reached, if we will inject more particles in the system, these particles will go to Bose-Einstein condensate. And this will be sharp peak at the bottom. And we apply more pumping power. Here pumping power was 1 watt. Here we'll apply 25 watts. And after that, we see, really we inject more magnons. Yes, here, dark area, in this case, much more smaller. Magnons appears at the bottom much more faster. Why? Because the density of injected magnons is here significantly higher. Probability for magnons to be scattered by each other is much more higher. And that is why they go to the bottom of spectrum in shorter time. But it's surprising that they don't go to the minimum. They stay here in this area for higher K numbers. No condensate occurs. Why? Explanation is such, is from our point of view, that we in such case, when we pump a lot of magnons, we increase not only chemical potential, we increase in addition temperature. And if we will calculate effective temperature at the bottom, it's simply density of magnons at the bottom. We can see that this temperature can be 30,000 Kelvin. It's higher than the temperature on the surface of sun. It's not phonon temperature. That is why we don't vaporize our sample. It's the temperature of magnons, which relates to the density of these magnons. And if we will increase the temperature so strong, no Bose-Einstein condensation can occur. But what occurs when we will switch pumping off? When we will switch pumping off, we see that magnons, which were previously concentrated in this area of spectrum, goes down in energy and goes to the global minimum and forms there a peak in density of magnons. So Bose-Einstein condensate appears in freely evolving, parametrically overpopulated gas after the pumping pulse is switched off. Why? We can understand this such situation as a cup of coffee, that there is always vaporization, the most energetic molecules going out. And in such case, temperature of coffee drops down. And the same occurs with these magnons, which we will inject in our system. Spectrum of our magnons is very huge. It's up to hundreds terahertz. And we inject magnons at the lower energy area of spectrum. So we inject a lot of magnons, but very cold magnons, low energetic magnons. And these magnons, due to the scattering, can go in the upper areas of spectrum. And these look such as vaporization. of magnons, vaporization of the area of parametric equilibrium, which is characterized by so high temperature. As a result, temperature drops down, but quantity of magnons not change so strong, because which magnons are vaporized? With highest energies. And that is why we decrease the temperature and obtain here Bose-Einstein condensation. So here Bose-Einstein condensation occurs. This process is dedicated by us as a supercooling of strongly heated low energy area of the magnon gas. It you can find in this publication. And if we see that condensation of magnons occurs after the pumping is switched off, we mostly investigate this area. It is very good area because when pumping is applied, I told that it's manipulated with bias magnetic field, we always shake the ground state of our spin system. And when pumping is switched off, no shaking occurs. So the system now is in calm state and only relaxes, and you see here in logarithmic scale, this relaxation after the formation of Bose-Einstein condensate, this peak up, here it's here, is completely linear in logarithmic scale, linear, and this means that relaxation is exponential. It's relaxation pure exponential to the lattice, to the phonons. And here we investigate freely evolving magnon Bose-Einstein condensate. And now we are going to the supercurrents. It's clear that in Bose-Einstein condensate of such types as condensate of Cooper pairs or as condensate of atoms of gallium-4, there are such viscosity-free motion and there is superconductivity. And I should say that superconductivity or viscous free motion are not important themselves. What is important that these motions are excited not through the external force, but they are excited due to the change of phase of wave function. We change the phase of wave function, and this change of phase, gradient of phase, propels the motion of condensates. That is why this is supercurrents. So supercurrents, it's flow of particles due to the phase gradient of condensate wave function. Can we reach this phase gradient in our case? Our BEC here, described by complex BEC wave function, here with the BEC density NC, it is here, and BEC phase here. Supercurrents from solution of the Gross-Pitayevsky equation, classical solution, here depends on coordinate, depends on time, and can be described by such simple formula where here we have mass of magnon, here we have Planck's constant, here we have BEC density, and here we have the gradient of BEC phase. And this BEC phase, how we can change? The simplest way from our point of view, it's change the magnetization. Magnetization of our sample. Magnetization we can change due to the change of temperature of the sample. Temperature higher, more thermal magnons are excited, thermal, not parametric magnons, thermal magnons with very high frequencies, and it's reduced magnetization. When magnetization is reduced, it's also causes the change in the frequency minimum. It's approximately 30 kilohertz per Gauss, and 4 Gauss per 1 Kelvin. So I change 1 Kelvin, it gives us 4 Gauss change in the magnetization. It gives us approximately 1 megahertz change in the 100 megahertz, not 100 kilohertz change in frequency. Very small frequency change. If you see that frequency itself, it's around 5 gigahertz, and here only kilohertz. And such, if we change frequency in course of time, we have phase accumulation. And here you see this animation with probing laser beam. We probe our condensate with laser beam. We change frequency locally. Here is a real photo using the infrared camera. We change the temperature here. As a result, we change frequency and introduce the phase shift in the condensate. By changing probing laser power or laser pulse duration, it is possible to control the phase of the magnon BEC. And let's look, I told that we can change power and duration of the pulse. And here you see pumping pulse, 2 microseconds, and laser pulse is switched on a little bit earlier. Because we can, if we want to hit the sample, we can switch it earlier, and earlier. And here we switch it after some time when we stop our analyzing of behavior of Bose-Einstein condensate. Such, and the first laser power duration 6 microseconds, power of laser power is rather small, 0.4 milliwatts. So practically no heating occurs, and that is why no supercurrents are expected. And we see here poor exponential decay, linear in the logarithmic case. If we will increase laser power, probing laser power to 10 milliwatts approximately, you see the change in the relaxation dynamics. Okay, we don't know why. Let's perform our experiments more. Let's don't change the power of probing laser beam, but change the duration. Longer. We'll switch it earlier, and earlier. And we will hit this probing point stronger, and stronger. And you see that relaxation dynamics is changed more and more. But in these relaxation dynamics, there is two interesting features. The first, relaxation increases with increase of temperature in the probing point. But only relaxation increases for well-populated gas. For small delays, here, for initial times, if you will wait some longer time, you see that relaxation dynamic starts to be the same. You see that these curves, it's only lines with the same slope. It means when the density of magnons falls down, when density of magnons is high, we have faster relaxation. When the density of magnons is smaller, in spite of that, the temperature is high. We see that there is this standard relaxation dynamics. Why? We can conclude that this faster relaxation dynamics due to the relaxation of BEC, and here slow relaxation dynamic due to the relaxation of incoherent magnon gas when BEC doesn't exist anymore. Okay, to describe this process, we have used system of balance equation. Balance between what? Between the externally injected magnons and density of parametrically injected magnons here. Density of magnons in a magnon gas, incoherent magnons, density of Bose-Einstein condensate, and density of magnons around Bose-Einstein condensate. Why we should say about density of magnons B around Bose-Einstein condensate? Because our frequency resolution and our vector resolution is finite. And that is why we are not able to see only Bose-Einstein condensate, only coherent particles. We see always this Bose-Einstein condensate with surrounding particles. That is why to properly analyze our experiment, we should take these two species. And okay, what occurs here? Here's the first, change in this time density of gas, surrounding incoherent magnons around Bose-Einstein condensate, and change in density of Bose-Einstein condensate. Why they change its density? Due to the damping. Here, standard damping to the lattice. Also, they change their density due to the scattering process. And this first one, gas is populated by parametric magnons. I inject magnons by external magnetic field, and these magnons scatters and increase the density of gaseous magnons here. After that, these gaseous magnons scatters. They scatters to the surrounding area around Bose-Einstein condensate. Surrounding magnons, when their density is high, scattering back. It's also these two terms should be taken into account. The same is here for bottom magnons. They are depopulated due to the damping, populated due to the scattering from magnon gas, depopulated to the back scattering to the magnon gas, and also they are depopulated due to the scattering to Bose-Einstein condensate. Magnons not scatters from one point to another because it's an isotropic spectrum where should satisfy energy conservation, momentum conservation laws. That is why scattering exists on the short distances. And here the scattering to the condensate. Only this scattering is possible above the threshold of Bose-Einstein condensate formation. So here is Heaviside function where he has a critical density for scattering to Bose-Einstein condensate. And Bose-Einstein condensate density also decays. It's standard magnons, and also they are populated due to the scattering from the surrounding magnons. And here 3 equations which are described by such diagram. Here to phonon Bose decay, and here the scattering between the different group of magnons. And if we are speaking about supercurrent, we should also introduce here additionally flowing of Bose-Einstein condensate out from our point of registration. Our point of registration is approximately 25 micrometers in diameter. Okay, this is what we have described here. It's without any thermal gradient. We can assume that thermal gradient exists. We induce phase, and as a phase gradient, as a result occurs some flowing of magnons from the area of registration or to the area of registration. It depends on the gradient sign. And here stays the gradient in the current. Here, and this current, as I told, supercurrent, depends on phase gradient in our Bose-Einstein condensate and density. And here mass of magnons. Mass of magnons we can easily calculate it when we know the spectrum of magnons. It is such formula. Here the dispersion of magnons, the second derivative from frequency respect to the wave number. Here the magnons. So the higher second derivative, here that lower magnon mass. It is interesting. Such, and we have introduced here all functions. Okay, in our case, two-dimensional case, it's a film. Supercurrent from flow in x direction across the magnetic field, and in y direction along the magnetic field, and all others direction. Should we solve this two-dimensional problem? Principally, yes. But if we remind us that we have at the bottom anisotropic dispersion spectrum of magnons, and this dx second derivative here, which gives us the mass of magnons, and dy are described by such equations, and currents depends on them. And if we will look what is the ratio between dx and dy, we see that dx, so the dispersion coefficient across magnetization direction, is 20 times higher than along magnetization direction. It means that supercurrent across magnetic field should be 20 times higher than supercurrent along the magnetic field. And you can see why it occurs. Here it's part of spectrum of magnons at the bottom, near the bottom. And this blue curve gives you the dispersion line. You have already seen this dispersion line along the magnetic field. But you see how anisotropic is spectrum. In the area of minimum, across the magnetic field, this surface is much more steepened. And that is why for this red curve, dispersion much more higher. And that is why we simply should look on the current which flows across magnetic field due to this reason. So we will go to the one-dimensional problem. Here in one-dimensional problem we have here one-dimensional thermally driven supercurrent. Here is a gradient of phase, and phase is a result in change of frequency due to the change of magnetization, as a result change of temperature and multiplied with time. Here current flows in one direction across the magnetic field. So, and if we will solve this problem, what we will see? The first, without any heating, we can fit our experimental curve. There is many parameters which we don't know in our system. It's efficiency of four-magnon scattering, for example, in our specific system. Efficiency of scattering to Bose-Einstein condensate. That is why what we are doing, we suppose there is no thermal gradient, there is no supercurrent, there is only our system which is described by balance equations, and we try to fit this system. And we will fit this with this black curve. Fitting is rather good. And after that, we will switch on frequency shift in our system as a result of heating. And frequency shift is initially 0 kilohertz, after that 25, 100, up to half of megahertz. And after that, we change nothing. We only introduce in the system which is already fitted by this black curve, we introduce only change in frequency due to the heating. And you see how this theoretical fit with so simple model works good. Here the density of magnons as function of in the Bose-Einstein condensate and with magnons surrounding it as a function of time. Okay, this maximal shift here, it is corresponding to maximal temperature change approximately 5 Kelvin, very small. And also, we are not able to measure this change in so small area as 25 micrometers. But we used COMSOL simulation software using 3D heat transfer model to calculate this. And from our calculation, temperature change for given laser power and duration is approximately 6 Kelvin. So it's rather good coincidence. And we also estimated supercurrent velocity. In our estimation, some such, it's approximately 300 meters per second. And now we can say that observed dynamics of magnon condensate can be understood taking into account magnon supercurrents. But this, you see, this observation, they're not direct observation. So we observe some relaxation dynamics, we build some model, we try to apply and make such conclusions that it should be magnon supercurrents. It is published in Nature Physics in 2016. So our arguments were accepted, but it would be good to have additional evidences. And such, in 2012, it was published the article of Sergei Demokritov. Professor Odonets Romero knows him, and Dr. Demidov, and also their postdoc Dzepko, also from the group of Professor Melkov, I should say, from Kyiv University. When they using the micro-BLS with very high spatial resolution in space, they investigated the structure of Bose-Einstein condensate to estimate if if really these dense magnons, which we see there at the minimum of spectrum, they are really coherent or not. Because if not coherent, it's only increase in density. They should be coherent for Bose-Einstein condensate. And they observe such interference structure. Why this interference structure appears? You see the spectrum of magnons is symmetrical. So there is a magnons with minus k Bose-Einstein condensate wave number and plus k Bose-Einstein wave number. So they should interfere. They should form such structure. And this is structure. And here there is modeling. And you see that in structure there is some artifacts, and modeling there is some artifacts. And this can be described by the coupled generalized Ginzburg-Landau equation. And these are vortices which occurs in the supercurrents. They not recognize it as a supercurrent at that time, but so it's additional evidence. And we'd want to see the transport. If there is supercurrent, it means current. It's something moves somewhere. Is it able to detect these currents, not only the change in density of magnons in one point? And for this, we have modified our system, improved this using the additional heating laser here. And this heating laser hit some spot in our sample. It's our microstrip resonator here from gold. Here on the top, there is yttrium-ion garnet film here on the top. Here is the probing spot, it's as previously from this, and we can scan. And on the scanning stage mounted the heating laser. It moves together with the sample. And that is why the heating spot here, we use blue laser. Blue laser better absorbed by yttrium-ion garnet. It's the first. The second one, it's not interfering with is our green light, which we used for measuring of density of magnons, and this heating spot. And after that, we will scan in such direction. You see, we will scan across bias magnetic field in that direction where the supercurrent, as we have calculated previously, should be maximum. Moreover, we scan along the resonator, so we will scan in the area where the pumping conditions are rather uniform. Moreover, we scan along the resonator, and I told for wave vector resolution, light should be reflected from resonator. And here, it can be reflected in all positions with practically the same efficiency. And what we will see, if we will stay exactly in the heating spot, it's 0 micrometers position, it's exactly in this, when green point and this blue point stays in the same special position, what we will see? We will switch pumping off, and we'll see some drop up in density of magnons and very fast decay. So similar to that what we observed previously. After that, for lower densities, decay is smaller. So nothing new. When we will stay apart, 100 micrometers from the center of the heating spot, we will see the stronger increase in density of magnons, fast decay as previously exactly, and after that, when density of magnons is small, lower decay. But if you stay 200 micrometers apart, second peak appears here. First peak, it's formation of Bose-Einstein condensate. What is the second peak? Let's stay even longer distance apart from the center of heating spot. We see that this peak is shifted in time. When we stay here, 400 micrometers apart, peak is shifted even more. So that magnons, which are pushed out from by supercurrent from the hot spot by gradient in phase, moves in the Bose-Einstein condensate, and when they are reaching the area of detection somewhere here, they form the additional peak. Here it's calculated temperature distribution by this commercial software console, 40 Kelvin heating, laser power 116 milliwatt heating laser power. It's permanent heating. We don't change laser power. We only switch off pumping power. And what occurs? You see formation of the low density area in the heated area, formation of two peaks of Bose-Einstein condensate, which propagates in one direction from the heat area and in another direction from the heat area. It's experimental data. Formation of condensate, and only when condensate is formed, phase is important, because when condensate is not formed, it is clear no predefined phase exists. There is no sense to say about the phase shift. So such shift. Here is one question. I told that supercurrent is excited due to the phase gradient. Phase gradient we form in the area of temperature gradient. But here you see that this temperature gradient area is rather narrow. Okay, maybe 100 micrometers in each direction. And after that, our pulses propagates long distance, half of millimeter, in the rather uniform temperature, where the gradient is small. Why? It contradicts with our model that motion is propelled by phase gradient. Moreover, I should say that from this nearby edge, you see that it's not symmetrically placed sample respect to the hot spot, that the pulse which propagates in this direction reflects. When we analyze deeper data with lower intensity such, we will see that this pulse propagates, reflects from the edge and propagates back. So not along the phase, along the temperature gradient, not in opposite direction to the temperature gradient, but along the temperature gradient. Moreover, the velocity of propagation is practically the same. Why? And what we can estimate the distance of propagation using this peak for different moment of times, and you see such dependencies. You see that our pulses propagates practically with the same group velocities. I don't know if it's group velocities, with the same velocities for different heating laser powers. Also, we can calculate here the width of the BEC pulse which propagates. And I should say in advance that the width depends on the intensity of BEC pulse, but velocity not depend. Why? And what we try to do, with the help of our collaborator, especially with help of Professor Lvov from Weizmann Institute of Science, we write down the Gross-Pitaevsky equation for dynamic behavior of the magnon BEC. It's Gross-Pitaevsky equation, the standard one. Here the wave function of our BEC, dependence on time. Here dispersion coefficient in this direction across the magnetic field. Here the this gradient. Here we will see that V, where this nonlinear coefficient, as you are very familiarized with this, when Professor Donitz Romero investigated formation of solitons, bullets in a group of Karl pattern. Here it also was used such equation, which was named as nonlinear Schrodinger equation. Gross-Pitayevsky and nonlinear Schrodinger equation, it's the same, only Gross-Pitayevsky equation is solved in non-uniform potential. Such, and after that we will place here the amplitude of four-way repulsive interaction. Why is repulsive is described in this article of Professor Slavin, Tiberkevich, and Alexander Dzapko from the group of Democrito. And stationary solution, its known stationary solution of such equation can be given in such a form. So where NC, as previously, it's magnon back density. It is interesting that on the background of this stationary solution can appear oscillation of density. So known Bogoliubov waves. So when density of Bose-Einstein condensate, which is described by this equation, changes in time and in space, and phase also changes. Such oscillations, it looks such that oscillation of superfluid phase in helium-4, for example. And these Bogoliubov solved this problem, and there is the dispersion law for small perturbation on the background of this stationary solution is described by this equation. And you see that this equation can be split in two parts if we will look on ratio of these two terms, here and here. In one case, it will be linear dispersion as a sound, when frequency linearly depends on wave number, with some coefficient Cs, what is the second sound velocity. And in another situation, it will be quadratic dispersion law. It's not the sound in such case. So we should estimate which from these two conditions are satisfied in our case. And how we can estimate this? We can measure the velocity of our peaks. It's, in our case, 450 meters per second. You see, it's very close to our first estimation from the relaxation dynamics. Here's a direct measurement of propagation of the peaks. We can calculate dispersion coefficient, because we can calculate the spectra of spin waves precisely. When we knew this parameter and this parameter, we can calculate also nonlinear frequency shift. And this nonlinear frequency shift gives us 44 megahertz. For 160 milliwatt laser power, the back BEC pulse width we can measure here. And this is approximately 44 micrometers. And when we have these 44 micrometers, this delta, we also can calculate carrier wave number for this pulse as P over the width of BEC pulse. It's the first component of special Fourier transformation. It will be Q approximately 720 radian per centimeter. We place it here. And we place there our dispersion coefficient here and calculate this species now. And you see that this only half of megahertz here, 44 megahertz here, half of megahertz. It means that this is well satisfied. So we have second sound. A second sound is oscillation of phase and density of Bose-Einstein condensate. If it's the second sound, it means that pulse, which is formed, wave can be its wave, but this wave can be in form of pulse. It's not harmonic wave. And this wave second sound velocity must be independent on the excitation conditions. For example, on the thermal gradient. And the heating, that means on the heating laser power, which determines the back BEC pulse width. BEC pulse width depends on the heating laser power because it's how strongest supercurrents which pushed magnons or BEC magnons out of the hot spot. And after that they will form peak, and this peak is narrower when the heating is stronger. And after that this peak propagates with the second sound velocity, which should estimate this. The first, we will see 100% change in the width of BEC pulse gives us, from experimental measurement, approximately 10% change in the velocity. It's good. Moreover, during the pulse propagation, the amplitude of the background condensate decays, and the sound velocity also has to decay. Here, sound velocity, here the density of condensate. And we can, using this equation, perform the fit of our experimental data from this parabolic equation, and we will see that this fit is rather good. So the sound velocity really decreases, and this decrease is clearly visible from parabolic fit of such. And both statements are well satisfied. That is why we can now say about the physical nature what we observe. The first, in the heating area, it's integral picture of our experimental data. Magnon supercurrents are propelled by local heating of the yttrium-ion garnet films, and supercurrents exist here and push magnons from this local heated area. Formation of non-uniform special distribution of magnon BEC due to these supercurrents results in the excitation of magnon second sound as a shock wave. Magnons pushed by gradient outside from the probing point, hot probing point, and as during the pressure forms these two waves of second sound. And these waves are formed here and propagates up to the edge of the samples. From this side, it's even reflected and propagates back. Second sound pulses propagate long distance path through the temperature uniform yttrium-ion garnet areas. So it's our vision, it's the last data, which are still not published. Only my own archive, there is some, but formation, so I will go to the summary. Formation of magnon Bose-Einstein condensate due to the evaporative supercooling of parametrically overpopulated magnon gas occurs here. Enhanced relaxation dynamics of a locally heated BEC as a result of supercurrent-related magnon outflow from the hotspot is observed here, you see. His demonstration is done of a non-local spin transport by magnon supercurrents in room temperature magnon BEC, and second sound scenario for the long distance supercurrent transport is proposed. So that's all what I want to present to you. Thank you very much for your attention.
Well, I think we have some time for questions.
Thank you very much for a very nice and clear talk. I'm wondering if you shape in some way the heating laser, for instance, can you, let's say, set a path of the supercurrent?
Yeah, I should say such that we do experiments now. There is different type of experiments. First, we would like to check this assumption about one-dimensional character of this supercurrent. In reality, it should be two-dimensional. That is why first we perform two-dimensional scan. It's not so easy. Here is microstripe. I told that when we move along the microstripe, everything is okay. But we should generate two-dimensional Bose-Einstein condensate in the long distances and scan around and check how condensates move. The second one, we'd want to use to shape laser power, as you told, in the distribution of laser power, to create some thermal landscape. And this thermal landscape in the simplest form, for example, it's two hot spots, which can excite these pulses in the opposite direction, and we would like to check the ability of interference of them. It's the first. It's not so simple because it's the question you see. We will repeat in pulsed regime, and that is why we should see the interference. The phase should be preserved from pulse to pulse. It's not so easy task. And also we'd want to use so-called laser special modulator to create some complicated landscapes, thermal landscapes, and check. It's from this point of view. Another one approach, it's create gradient not of the magnetization, saturation magnetization due to the heating, but to create the gradient of bias magnetic field. Such gradient can be positive and negative. We can increase locally bias magnetic field and decrease. So we can expect that supercurrent flow not only from this area, when the gradient will be introduced, but also to this area. But it should be still checked.
Thanks for your talk. Maybe a very simple question. From the data you show of supercurrent propagation, is there a direct way of distinguishing between a supercurrent and just a normal magnon current? Or could you actually look at the interesting properties of a supercurrent, like non-dissipation or anything like that?
No. Here it's such. You see that we perform the observation in the area where the group velocity of spin waves is 0. So that, okay, it is such when we are speaking here about the dispersion coefficients, it's really we smash the group velocities, but it's in the stays in the Gross-Pitayevsky equation, principally such. And moreover, you see that our propagation in the minimum, this stuff in the minimum, which should not propagate. It's Bose-Einstein condensate. If you apply no gradient of temperature, we already performed such scans. We see that it's always on the same place, stays. And here, also, it's interesting that in our case, propagation not in the length of k vector, but across direction. It's clear that these answers, what I am saying, it's a good hints to associate this with a supercurrent, but it's not enough. We need additional studies. Such a case, even to check additional studies to check the order of coherency of Bose-Einstein condensate, because it's in course of decay, coherency order falls down. Such, moreover, we see here not only supercurrent flow, but also we see here should see some diffusion motion of thermal magnons, no, not thermal, let's say such incoherent magnons, such motion. Here it can be the question, our supercurrent, normally if we will use two liquid model for helium-4, density of supercurrent increases, density of Bose-Einstein condensate increases, superfluid part, and density of normal part decreases in antiphase. And this is a thermal wave. Yeah? In our case, the question, density of Bose-Einstein, the density of condensed phase decreases. Why it's not, this density decrease not compensated by gaseous magnons, as in two liquid model. And answer is such that diffusion motion we have estimated much slower than this supercurrent motion. So simply there is not enough time for compensating. That is why it's not antiphase motion. The magnons really density, total density of magnons really decreases there. Oh, it's not that second sound as in helium-4. It's another type of second sound as oscillation of density of condensate, which is not compensated by antiphase motion of normal phase.
Another question? If not, we clap again.
Thank you very much.